Hello students, today we will be dealing with the variation of the pressure with depths in the liquids. Now while we are dealing all of these concepts of the fluids, one thing should be kept in mind that all of these properties are valid only for the ideal fluids, which we have seen what exactly is it. When it's incompressible, that fluids are called the ideal fluids. So let's see how the pressure varies with depth within a fluid. Now we'll be dealing with a new topic called the fluids at rest and Pascal's law. Now let's see what happens when consider the mechanics of the fluids at rest. Now here we are considering the situation when the fluid is at rest. This should be kept in mind. This whole of the operation that we are going to do will not be valid when the fluid is in motion. This is only when the fluids are at rest. When the fluid is in motion, you cannot apply the formulas that we are going to get or the equations that we are writing like this. All these formulas won't be correct. This is only for the fluids at rest. This should be kept in mind. Now let's see what we have considered here. We have considered a cylinder. This cylinder contains fluid. Okay. Now within this fluid we consider an imaginary cylinder. Consider a part of this cylinder. Consider, suppose this is A, area of cross section. This is depth. We consider a cylinder like this. Within this whole uniform large cylinder. Now this whole cylinder is at rest. This is in equilibrium. The liquids are not moving. That means if you consider any part of it, cylinder like this, of this depth, this is also in equilibrium because the whole system is in equilibrium. So every part of it here, as you can see, this is also at rest. All parts are at rest. So they are also in equilibrium. Now if we assume that the pressure that is acting at the top is P naught, what will be the force that will be acting on this portion? This portion of the imaginary cylinder that I have considered. So if A is the area of this, P naught is the pressure that is acting on the surface throughout. On the area A, the force that will act is P naught times A. This is the force that is acting from the top. Okay. Now if we assume that the pressure at depth D, which is also the length of the imaginary cylinder that I have considered. If I assume that the pressure here is P, now the force that will act here is P into A. This is the force from the bottom. Okay. Now is there any other force that's remaining? Yes, it's the weight of the liquid. So what is the weight of this column of the liquid that I have considered? Now to find out the weight, now if this is of this depth, it will have a smaller mass. If it is of larger depth, it will have a larger mass. If its area of cross section is this and the length is fixed, then this column will have some weight. A larger area of cross section will have larger weight. So it depends on the dimensions that you have considered that will give you the mass. So now the dimensions that we have here is A and D. What will be the volume of this? Volume will, A is the area of cross section, D is the length of the cylinder. So this is the volume of the cylinder, this imaginary cylinder that I have considered. What will be the mass? Mass will be A into D into G. Sorry, A into D into rho, because mass is volume into density. Okay. So this gives you this mass. What is the weight of this liquid? If mass is M, weight will be mg. Mg, and the pressure forces that we have written is this. Now what are the forces that are acting downward? It's P naught A that is acting downward. Then there is your weight mg that always acts downward. So P naught A and mg both are acting downward. And it's P into A that is acting upward. The pressure from the bottom, it will act in the upward direction. Okay. So the pressure acting on this section is actually upward, which is magnitude P into A. So the net forces that are acting downward must be balanced by the net forces that are acting upward, because this cylinder is in equilibrium. It is in a static equilibrium. Then from the Newton's first law, net forces on it should be 0. That means if we draw the free body diagram like this, PA is the upward force, P naught A is the downward, mg is the downward force, and Newton's first law gives you this because it is in a static equilibrium. So if you balance the forces, we will have P into A that is acting upward is equal to P naught into A plus mg acting downward. These are the net forces that are acting downward. Now let's simplify this a bit. Mass, we know, we have seen this is rho into A into D into G. If you cancel out the G, the A, not the G, you cancel out A and A, what you have is P is P naught times rho G into D. So what is the P? If you remember, this was the pressure at the depth D. So the pressure at the depth D is P naught, that is the pressure at that height, initial height, the surface, plus rho g into d. Rho is the density of the liquid, g is the gravity, d is the depth of point where we are calculating the pressure. This is called the hydrostatic pressure at depth d. Now this single term rho g d is also called gauge pressure. Now this is a terminology that you should know. So if rho g d, if the gauge pressure is being asked, you don't have to find out the total pressure. What you have to find out is P minus P naught only, because this is rho g d. If you bring P naught on this side, this is rho g d. So rho g d is actually the change in pressure that is acting when you move a depth d. So this is called the gauge pressure. Okay. Now let's see some questions here. Now if you see here, an iceberg floats in a shallow sea. Can you say about the pressure about points 1 and 2? What can you say about the pressure at points 1 and 2? Now as you know that the pressure in a liquid, it depends on the depth. What is the depth? Suppose if you consider this, d is the depth from the surface. If you consider the pressure here is P naught, what will be the pressure P at this point? Now we know that pressure P is P naught plus rho g into d. Okay. Now if you see that for both the points 1 and 2, the depth from the surface of the liquid, what you have to consider is the depth from the surface of the liquid. Okay. Now depth from the surface of the liquid is d only for both of this. What that means is that the pressure in a liquid, at the same depth will give you the same pressure. If the d is same, the P will be same for both of the two when you are considering the same liquid. What is important here is this again. If the liquid is same, that means the density for both of, if you consider this 1 point and 2 point, for 1 and 2, both of these, the liquids are same, in the same liquid they are kept. That means the rho will be same for both of this. G will be same for both of this, it doesn't depend on it. And if both are on the same depth d, the P that you will get, the pressure at 1 will also be P naught plus rho g d. The pressure at 2 will also be P naught plus rho g into d. So you get that the pressures are same and the correct answer is P. Now let's see this question. Is this possible? Is this situation possible that this is D2, this is D1? Now you can see it from here, this is like this. This is height larger than this height. Suppose the pressure at this point, since this is open to the atmosphere, we assume that the pressure that is acting here is atmospheric pressure, that is P atm. This is open to the atmosphere. Same thing is happening here. This is atmospheric pressure. Okay. Now, if we apply the formula that we have got there, suppose this is some distance d. Okay. If this is some distance d, the pressure that is acting here is P atm. If we apply the equation that we have got, what will be the pressure at this point? Make this point as P. The pressure at this point P will be P atm plus rho g into d, where d is this depth. Because here the pressure is P, at a depth d, we will have the pressure is P atm plus rho g d. Now if you see here that this point and this point, because this is at the same level, these 2 points are at the same level in the same liquid. These 2 points are at the same level in the same liquid. What that does mean, what this means is that this must be equal to the pressure at this point, because the pressure at the same depths within the same liquid must be same. That means pressure at this point must be equal to this. This must be equal to P atm. What this means, this equation can only be true when d is 0. So the only situation that is possible is when both will have the same height. This situation is not possible. This equation will be true only for d equal to 0. So this is not possible. Now let's see this question. What can you say about the pressures at the points 1, 2 and 3? This is point 1, this is point 2, this is point 3. Now if you see from the figure, it gives you that point 1 and 3, they are almost at the same level. This is 2 is here. Okay. Now suppose the pressure at 2 we denote is P naught, and this level where 1 and 3 are located is at a depth d. If we write the pressure P at this level is P, what will be that value? P will be P naught plus rho g d. Now this P will be present both at the point 1 and both at the point 1 and 3. Pressure at 1 and 3, because they are at the same level within the same liquid, so the pressure at this point and this point are same, but the pressure at 2 is P naught. Now the pressure at 1 or 3, we see it is greater than P naught. If you see from the equation, rho GT is a positive value. That means the pressure at 1 is equal to pressure at 3 and both are greater than the pressure at 2, which is atmospheric pressure. So students, we have seen how the pressure varies with depth. In the next class, we will be dealing with some of the instruments, devices that use the principle based on the pressure variations. The instruments that we will be primarily discussing will be manometer, the barometer and the hydraulic lift. So stay tuned with Ask IITians for the next topic.